I'm Wil McCarthy, Futuresmith. I'm the author of Rich Man's Sky and other science fiction novels. You can find out more at futuresmith.com. So called hard science fiction is fiction where the science is correct, or at least sounds correct enough to satisfy a demanding audience. In this series, we'll explore how I've used simple calculations in a spreadsheet program to work out technical details for science fiction novels like Rich Man's Sky. Okay, today we're going to be studying the acceleration of an object in a straight line. Maybe it's a spaceship. Maybe we're writing a science fiction story and we want to accurately determine how quickly our spaceship gets around. Maybe it's a homework problem. It doesn't really matter why you want to model acceleration in a straight line. It's a very straightforward thing to do using Microsoft Excel, so we're going to do that. Um, and we will start by having some definitions. We have the mass of our spaceship, which is m. Acceleration is a. The velocity of the ship is v, which is simply acceleration times time, or at. The distance that we've traveled is d, which is velocity times time, or 1/2 acceleration times time squared, 1/2 at squared. Uh, And we can also measure the kinetic energy of our spaceship, which is 1/2 mass times velocity squared, or 1/2 mv squared. Now, we can do this with a very simple Excel spreadsheet. We have a number of columns. We have time, which we're going to measure in days. We have acceleration, which we're going to measure in meters per second squared. We have our velocity, which we'll measure in meters per second. And we have our distance, which we're going to measure distance in astronomical units, but we'll get to that a little later. Um, by measuring our speed in days, we've got day 1, day 2, day 3, all the way through day 10. And the reason we're measuring in days will be apparent in a minute here. Uh, the acceleration we're going to measure in meters per second squared. Um, so we've got 1 meter per second squared for our acceleration. Um, and that's a very gentle acceleration. It's 1/10 of a g. It's 1/10 of the acceleration that you experience standing on the surface of the Earth. Your car can accelerate faster than this. So this is an acceleration that uh, to you would feel very gentle. Uh, and how much speed does this acceleration add? Well, over the course of a day, um, we have 1 meter per second squared that we're adding. How many seconds are in a day? Well, there are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day. So we just take our acceleration times 3,600 times 24, and that gives us our change in speed, which is 86,400 meters per second, uh, or 86.4 kilometers per second. And that's pretty fast. That's faster than a comet travels. So at the end of just one day of this fairly gentle acceleration, we're already up to interplanetary speeds. So that's pretty exciting. But in fact, we add this same amount of speed every single day that we travel. We're going to add 86.4 kilometers per second every day over the course of 10 days. Um, so at the end of the first day, we've got 86,400 meters per second. At the end of the second day, we've got twice that, then 3 times that, all the way down to day 10. On day 10, we've got 10 times that uh, speed, which is 864,000 meters per second squared, or 864 kilometers per second. Uh, uh, so that's very fast. That's 0.3% of the speed of light. Uh, so for zipping around the solar system, this is a very nice sort of Buck Rogers speed. Um, Now we can also measure that speed in astronomical units. An astronomical unit is simply the distance between the sun and the Earth. Uh, It's also about 8 light minutes. When light is emitted by the sun, it takes about 8 minutes to travel from the sun to the Earth. So the radius of Earth's orbit is 1 AU. The diameter of Earth's orbit is 2 AU. Um, and you can see at the end of that first day, in terms of astronomical units, we haven't traveled very far. Uh, but by the end of the 10th day, we're going half an AU uh, every day. So that's a very nice, very fast interplanetary speed. And if we look what that does to distance, again, at the end of that first day, we've only gone 0.025 AU, not very far in terms of the scale of the solar system. But by the end of that 10th day, we've gone about 2.5 AU. So again, with this very gentle acceleration adding up over time, we've gone uh, 2.5 times the distance from the sun to the Earth over just 10 days. Now, that's interesting because the orbit of Mars is at 1.5 AU from the sun. And so that means that regardless of where Mars is in its orbit and regardless of where Earth is in its orbit, this 10 days is enough time for us to travel to Mars. Um, so that's pretty cool. The asteroid belt sits at 2.2 to 3.2 AU. So in 10 days, we can get pretty deep into the asteroid belt, though not all the way through it. Uh, and we will not, unfortunately, reach Jupiter. The orbit of Jupiter's radius is 5 AU. So at the end of 10 days, we won't have gotten that far. But what we can do is extend these columns down by one row, and we find that, boy, just one day later, we've gone 6 AU. So we've actually passed Jupiter on the 11th day. Uh, so really, it takes us just 10 days and a fraction more uh, to reach Jupiter at this very gentle acceleration. Now, what can we do with this? Well, we can determine what the kinetic energy is of that object. Let's uh, let's go back to day 10. Let's get rid of this row here and not worry about it. Let's just worry about day 10. Um, the kinetic energy, again, is 1/2 mv squared. To do that, we have to define what m is. Um, and I've chosen 1 million kilograms as the mass of our spaceship. That's about the weight of 3 fully loaded jumbo jets. Um, so it's heavier than a space shuttle, but a lot lighter than the Starship Enterprise. Um, so anyway, now that we know our kinetic energy, we can figure out how much fuel it's going to take us to get to that speed and that distance. Now we're going to cheat here, and we're going to use antimatter. Antimatter has the property, as you may know, of when it comes in contact with normal matter, it annihilates and turns into pure energy. And for our purposes here, we're going to turn it into pure kinetic energy. That's cheating too. Any real engine is going to have losses, and when we convert mass into gamma rays, we have to find a way to focus those gamma rays all in the same direction. Those are engineering problems that are beyond the scope of this discussion. We're just going to assume for right now that our spaceship engine is perfect, and it converts mass into kinetic energy uh, with 100% efficiency. So to get going to this kinetic energy here, this value of 1/2 mv squared, um, we can convert that into mass, an amount of mass that we need to consume using E equals mc squared. Uh, that means, of course, that m equals E over c squared. So this is our kinetic energy divided by the speed of light squared. And again, the speed of light is 3 times 10 to the 8th meters per second. So this tells us that we need to consume 4.1 kilograms of mass. And this is probably going to be 2 kilograms of matter and 2 kilograms of antimatter coming together. So that's a pretty good chunk. That's a fairly hefty chunk of antimatter that we require to this gentle acceleration over a period of 10 days requires a significant amount of fuel. Um, so that's just something that you might want to know if you're writing a science fiction story, or if you're doing a homework problem. How easy is it to do this gentle acceleration over a period of 10 days? Well, the answer is not very easy. Uh, uh, but anyway, we can use these same principles um, for a smaller problem. If we have, instead of a spaceship, if we have an astronaut in a spacesuit, maybe he's got a maneuvering unit that allows him to control the speed of the spacesuit. He's got jets on his back. Um, so now, instead of measuring time in uh, days, we're going to measure it in minutes. Instead of 10 days, we'll have 10 minutes. And instead of 1 meter per second squared, we'll have zero point 0.1 meters per second squared. So a very small acceleration, well within the capability of a spacesuit jet. So this is going to add 6 meters per second every minute. Um, and so then we'll find that at the end of 10 minutes, we're going 60 meters per second. That's pretty fast for an astronaut to fly unprotected. And if we look at the distance, uh, that means that we can travel 18 kilometers in 10 minutes at that very gentle acceleration. Um, so again, this acceleration adds up over time, and that's how we can model it using Microsoft Excel. Uh, that's all for this time. Please like, follow, and share, and we will see you next time.